Ducescu, and I am the General Director of this Institute for Nonmetals and Rare Metals, National Research and Development Institute for Non-Ferrous and Rare Metals. I would like to thank to all speakers, attendees, and we hope will be a successful event. This is the 8th EMERGEMAT conference. We started in 2018, and now we are at the 8th edition. The conference is focused on 4 sections: materials for energy, critical raw materials, new materials for environmental protection, materials modeling and simulations. I would like first of all to thank to the team who organized this event. It was a hard work, and I will start with this. Thank you again for the effort. I would like to thank all the attendees for their presence, physical and online. I wish everyone an inspiring and enjoyable conference. And now, the Nano Team and Alteo Moment sponsors moment, please.
Yes, thank you. Our current edition of EMERGEMAT is financially supported by the Ministry of Education and Research, by the European Technological Platform of Sustainable Raw Materials, and by 2 Romanian companies, Nano Team and Alteo. From time to time, we will remind you the group of sponsors of our event. With this short presentation of the sponsors, I have the pleasure to introduce once again our General Director, Dr. Piticescu, with her first presentation, IMNR in the context of Critical Raw Materials Act and Industrial Green Deal. May I ask you to sit here in order to have a very good sound for the online? Okay. It is better to please.
I want to mention that is the first time when the technological platform on sustainable raw materials is co-organizer of this event. We are members in this technological platform, and I would like to thank the members of the platform, especially to Marina Capdosh for her support. I will, with your permission, I will stay here in order to have a good sound. The presentation is focused on the approaches of IMNR in the context of critical raw materials and industrial Green Deal, because we are the only institute in Romania who implemented different technologies to valorize metals or their compounds from secondary raw resources. No, I can't stay.
Okay.
But I will stay here.
Towards the camera.
Yes. Contains IMNR, past and present, Critical Raw Material Act and Industrial Green Deal, some European documents, IMNR Strategic Innovative Solutions, and future initiatives. IMNR, past and present. So we have a history of about 60 years. The institute was established in 1966, then in 1990 was reorganized. In 2000 took place an asymmetric division, so the design sector is separated from the institute. Then in 2004, the institute became National Institute, National Research and Development Institute. And in this moment, we are accredited for 5 years as National Research and Development Institute, accreditation from 2023. Critical Raw Materials Act and Industrial Green Deal. So here are two important documents, but not the only ones. Regulation of European Commission from 2024. And here there are some important aspects. Access to raw materials is essential for union economy and the functioning of the internal market. Few third countries supply non-energy, non-agricultural raw materials, which have high economic importance. Critical raw materials have an important role in the green and digital transition. The risk of supply disruptions is increasing. So European Commission is focused on this aspect. Another document, European Commission from 2023, is a communication to the European Parliament, the Council, the European Economic and Social Committee, and the Committee of the Regions, and is focused on a secure and sustainable supply of critical raw materials in support of the twin transition. Just to know that demand for rare earth metals is expected to increase by 4.5 by 2030 and 5.5 times by 2050. And also lithium will increase 11 times by 2030 and 17 times by 2050 respectively. And in this communication from 2023, it mentioned strategic projects will be supported, will be implemented by the European Commission to cover the entire value chain, from exploration to the final product. Current market analysis here, managing exploration. So the first step of value chain, mining and processing, parts manufacturing, product manufacturing. We have the product. use and reuse, we have urban mine. Here, collection and pre-processing, it is a risk to lose functionality and some resources. End of processing, now we have secondary resources, and we go to parts manufacturing and so on. This is a value chain for minerals and metals. Historical mining sites, tailings, dumps, mine waste, where we have copper, lead, zinc, silver, gold, tin, stibbium, indium, tellurium, hydrometallurgy, bioleaching, and also pyrometallurgy. We can recover. Then we have manufacturing residues, slag, scrap, dust. Here we have steel, aluminum, copper, lead, zinc, titanium, nickel, chromium, vanadium, manganese, molybdenum, tungsten, and we have combined processes, and also we can use electrometallurgy. Urban mining, end of life, different electronic waste, battery, spent catalysts. So we have rare earths, lithium, and also platinum group metals by electrometallurgy. Current market analysis. So we have here metals, different metals, stibbium, indium, cobalt, graphite, platinum metal groups. Here is the challenge for every metal or group of metals. Spent magnets, neodymium, iron, boron, many processes, electronic waste, economic feasibility, slags with a low concentration of rare earths, silicon, end of life, solar pellets, which contains toxic solar pellets, which contain toxic elements such as lead and cadmium. I don't want to insist because the time is very short. EMERGEMAT strategic innovative solutions in this context. So our strategy for idea management, market research. So the first step is market research. The second step, idea, innovation, creativity. The third step, research activities development. And the fourth step, technologies and products and technological transfer where it is possible. Our technologies, energy saving, based on safe by design. And we are the only institute which implemented safe by design. Our new offerings here could bring added value to the end users. EMERGEMAT innovative solutions. The first one, additive fabrication. Here is the project MANUNET, acronym NIMF, in the period 2020-2022, partnership with Norway, with a small and medium enterprise from Norway and a small and medium enterprise from Romania. We obtain by additive fabrication, carbon nanotubes functionalized, and then processing, and we obtain these structures. This structures replaces electrodeionization, and also using Zortrax, we succeeded to fabricate this device where this um, uh, products are inserted and are used to um, um, uh, purify pharmaceutical products, pharmaceutical oils. Magnetic elements recover and additive fabrication. We use this equipment, which was fabricated during project funded by structural, financed by structural funds. We recover neodymium, and this was used by the coordinator, Factory Belgium, to obtain by additive fabrication this device. Neodymium was recovered from electronic wastes. Rare earth recovery and advanced fabrication. This was a project, Eramin project, financed by Eramin Call 2 in the period 2018-2021, and we recover all the oxides of rare earth, and we used this to dope zirconia for EB-PVD applications. The partners, Enea from Italy, a small and medium enterprise from Romania, and an institute from France. And here is the application. Lithium recovery. We are partners in this project. The coordinator is from Belgium. And here are the results and the contribution of IMNR to this project. The project will finish this year in December. Another project were high entropy alloys, and this project offers a solution to replace critical raw materials. It's a project financed by resilience and recovery plan. The period 2023-2026, and we have to offer solutions for this aspect, for example, ship, corrosion, and also other types of corrosion. So we expect these high entropy alloys, and the results are encouraging to be a solution. And another one, modeling and safe by design. Another aspect of a project financed by in the frame of Horizon Europe. Computational multi-models enable design of safe and sustainable multi-component high entropy alloys. The period 2024-2027 coordinator is from Spain, Navarra Industrial Association. And it's very important that we design physical deposition process using molecular dynamics, Medea materials design software. Here, an example of how to use this for the coatings. future initiative, product enhancement, technology integration, collaborative partnership, what we want to offer, green supply chain, reduce carbon footprint, waste reduction, water conservation. Thank you for your attention. And here is the Institute, the printer for metals, 3D metals, and here some medals obtained at the Euro Invent content. Thank you again for your attention.
Thank you, Dr. Piticescu, for your presentation. If there are any questions from the audience or from the online participants, right now it looks that we have an audience of more than 40 participants from online. Thank you, all of you. If there are no questions, the next presentation is done by Mrs. Simona Lacatoș from IRCEM, tehnologie emergente în economia circulară pentru ingineria materialelor, de la proiectare la valorificarea resurselor critice. Mrs. Lacatoș, can you hear us, please?
Yes, hello, I hear you very well.
Okay.
I want to ask you if you are see my presentation.
Yes, your presentation is right now displayed.
Can you
Okay, one moment.
But
put it in.
you can ask the computer to display full screen. Perfect, yeah.
Okay, great. Thank you so much.
Okay.
Hello, my name is Simina Lacatoș, and I represent the Institute from Research in Circular Economy and Environment. And sorry, because I took a flu and my voice is not so good like usually, but I try to do my best. Thank you so much for the invitation and for the opportunity to say something about the circular economy and the impact that have it in the material engineering and of course of the critical resource material also. Why it is this so important? Because I will take to the important things, because if we are continuing in the same way like now to use and consume, and if the number of population are growing in the same way, in let's say in 20 40 years, we'll not have the resources that we will have now. And if you hear this year, we end the resources for all the year much earlier than the last year and the last year too. That means that we cannot continue in the same way, and we need to change our habits. And the circular economy, let's say, it is one of the way in which we can change this and change the way in which we are consuming and producing from the linear economy to circular economy. But I will not insist more about this because the Mrs. Piticescu said something about the circular economy, the European Commission direction on the circular economy action plan and the Green Deal. And this is the policy that want to support us in this demand. And why? Because it's important to have focus in recovery our materials, raw materials especially, and I cannot say more about the critical raw material because, how I said earlier, our situation is not so pink in this moment. And why? Because we are consuming a lot of materials and a lot of waters, and we are producing a lot of carbon. And we can change this in closing the loop by recovering, recycling, reusing, and repairing. How? By developing a new type of material, substituting use, substituting kind. But how? By uh, starting with the technology, with material extraction, design and production, retail and distribution on the entire value chain. And why? Because we need to be more sustainable, more resilient, and more competitive on the market. Because on the end, we need to find a solution of our resources, and we need to let something for our, let's say, children and the children of our children. Why design of the for circularity is so important? Because the circularity, we find it in all the product. Even we are talking about mobile phone, I don't know, computers, or industrial technology. For all the, let's say, market, we can apply the design for circularity, for interoperability components to assure and let's say sustainability for all the steps for the raw material to the end. Why it's important the design for this for circularity? Because not only for the European Commission comes with regulation in this direction, but because it's important for our resources, because it and for our, let's say, economy. Design for reparability and disassembly comes with a lot of benefits related to uh, materials that are raw materials that will not be used on the future, carbon footprint that I said earlier, and of course, money for consumers. Design for remanufacturings for here I speak about the tolerance, surface treatment, part marketing. It's important for industry because we are seeing the effect of the climate changing and the impact of carbon footprint that we are making when we are producing our goods. Of course, design of recyclability. Here we are speaking of monomaterials, compatible polymers from families, and clean separation. It's not an easy way, but we have results. We have, let's say, companies that are doing this. And of course, design for substitution, how I said earlier, related to modular material stack enabling and for circular raw material substitution. And why? How we can do this? Because it's not easy when you want to use, let's say, repair it electronics, because sometimes the legislation is not clear for companies. And related to this situation, we need to develop this digital product passport, and of course FPRD that are related to the environmental product declaration. And in the last years in Romania, we saw some results in this part too, related to digital product passport. In the electronics components, some companies do this, and for this reason, it is important to have a traceability for what is happening with the product from the beginning, and we'll start with the raw material until of the end when this product become a new raw material, and he start a new cycle. And of course, here we are speaking the life cycle data container that are contain composition, origins, repairs, upgrades, recycled content, all this information that are appear to the label that this digital product passport will have it. Of course, machine rebel circular claim, audit trail for compliance and financing, and environment product declaration, how I said earlier, alignment for impact and comparability with different other products. Here I have another example of circular material passport and material pool flow for Gitwood related to some subconductors and what are the steps, what is the traceability, and what we want to know about these materials. I come with two examples for what I believe that it's let's say more focus in our today presentation. And the next one is related to battery passport that are related to the ESG principles, because right now everybody are speaking about the ESG impact, the do not significant harm aspect. And for this reason, I believe that it's important to take in consideration this aspect, even we are speaking not only about the projects that are financing by the European Fund, but it's important to have these principles in our products day by day, because not only about the let's say impact that we have about our earth, but it is important to know from where this product is coming, how we can do about this, in what condition was product, and so on. And here are some direction that this Global Battery Alliance analyze it and come related to battery passport. Of course, advanced materials are a key, let's say, steps in changing our way, because, how I said earlier, it's very important to come with new materials that can substitute in woods or in way the materials that we are using right now, and they are a very energophag and with huge footprint carbon. And for this, we need to, let's say, invest a lot in innovation, in developing new advanced materials. Even we are speaking about bio-based polymers, engineered wood with improved durability, high-tech recycled content metals, low carbon alloying, and so on. And we saw in the last couple of years that critical material tracking and substitution, for instance, rare earth material, become a very important, let's say, aspect in all the financing European funds and all the policy, because we saw the important that they have it in the, let's say, new condition that was in the world. We are speaking about the pandemic, we are speaking about the war that we have it close to us between the Ukraine and Russia. And in that period, we saw the importance to see how we can develop and have this critical material for different components that was very important from different industries. Of course, the manufacturing technologies, here we are speaking about the additive manufacturing for part level related to repair, hybrid manufacturing for cladding, laser metal depositing, solvent-based and depolymerization recycling, and of course, robotics for automated disassembly and sorting. I want to not insist more because my time is very short, but I want to say that critical raw materials and materials flow analysis with CRM, critical indicators, and recovery feasibility assessment and drivers for these are drivers for design for substitution and strategy stocks. And for this, I believe that the KPIs that matters are related to share of secondary content, value-based recovery, design for KPIs, performers, climate and footprint, CRM expose, of course, the last but not end, the financing, because without sustainability and financing for the company are not important so much. And here I come with some examples with some companies and in some countries where they see the benefits of circular economy related to design for repairability, recycled content, end of life for resources security, and here we are speaking for some IT computers that was reused in some companies or others was recovered, even in the social airport that we use the um, light as a service because how I said earlier, we need to change our behavior that what we think until now that the market go because we need to find other solution. Here are some examples related to the furniture where some even the school was using some recycled furniture or circular offices for Netherlands that they saw the impact and the necessity of this, and of course the company that invest in developing these new technologies. I continue with the construction sector, where design for the construction, recycling, of course, carbon footprint reduction was huge. And here are, of course, some example too, where the circular economy was integrated in new construction, renovated, textile and workwear are the same, are saying the benefits of circular economy. Even we are speaking about nursery uniform that was reused from different other textile that was used in the part of hotel industry. And I will say about food and catering, there are some other results, but I let this the last one because it's not the topic of today's meeting, but I want to introduce because it's important too. Conclusion, what are the future direction? What we need to do? Of course, advanced technology and innovation driver for efficiency, sustainability, and competitiveness in circular public procurement and in industry too. Circular trends in shaping future practice like blockchain, artificial intelligence, Internet of Things that are revolutioning the industry, the processes, and of course, circularity environment impact. Very important it is the ethical part, because sometimes we are forgetting about the ethical part because we want to innovate it, but of course the legislation will come, but I believe it's most important is to be volunteer, not regulated. The importance of the EU policy that are support us and promote the resource efficiency, eco-innovation, sustainable products or circular economy initiatives, and we are seeing different financing grants that are supporting this. And of course, circular economy application that are presenting in the Circular Economy Action Plan are supported by the European Commission. I want to say that the last things that I want to add, if you have projects, products that are related to circular economy, please go to the European Circular Economy Stakeholder Platform and say what is your project, what are you doing, or send it to us, because we want to promote this and show this that the results are happening, and the circular economy, it is very important in our life day by day. Thank you so much. And I want to say with, let's say, African proverb in order to conclude, if you want to go fast, go alone. If you want to go far, go together. Thank you so much for your attention.
Thank you, Mrs. Lakatos, for your very interesting presentation. If there are questions from the audience, from people here, present here in the hall, or from the online, it seems no. I hope that the Romanian society will understand each day better and better the importance of the circular economy for the future of our country. And let's hope that from starting from the large audience, from normal people to research industry and authorities, all these aspects concerning recycling and so on to be better and better understood. Thank you once again, Mrs. Lakatos. And before going to the presentations in section one, I will ask you for a small change in the schedule. There is a last-minute presentation. Mr. Năstuță, can you hear us? I understand that you are present online. Yes. Is he there?
We can see you, but we cannot hear you.
Mr. Năstuță, can you open your microphone, please?
Now I believe you can hear me better.
Yes, right now we can hear you. Okay, so
I will share my screen in a second.
okay.
Can you see the presentation?
Yes, but try to use the widescreen. Full screen view. Okay, like this. Thank you.
So, hello everybody. My name is Andrei Năstuță. I'm from University of Medicine and Pharmacy Grigore Popa Iași, Faculty of Medical Bioengineering, and I will speak about some things related to how electrical discharges can influence the properties of some polymers that we usually are using in the additive manufacturing processes. The thing is that even though we process plastic material every day in several industries, we still need to know how our products can be made better each day. And of course, we are trying to make this better process through some chemical-free scenarios. And in this concept, plasma discharges can help us in doing that. If we are talking about atmospheric pressure plasmas, usually we can think about some devices that can be used in medical field, or they can be used in processing material for food industry, for construction, automotive, and so on. Here I just will say very short that we can have these discharges in a broad range of parameters like voltages, frequencies, current, power, and we can use them in various mixtures of gases in order to fulfill our demands. Our setup that we used for these experiments involve a plasma jet configuration. That means we have a dielectric tube through which we have a gas flow, and applying a high voltage, we ignite a plasma, an electrical discharge. This plasma can be used in order to expose many materials to it by varying some electrical parameters to the plasma. We are good at diagnosing these plasma sources electrically and optically, and by doing that and varying some plasma parameters, we can tune up a little bit the effect that we will have upon the material that we are using it for the study. Going further to this electrical diagnosis, we can say that our discharge can be up to several tens of watts of power. That will mean some millijoules of electrical energy, electrical current upon of tens of milliamps, and of course the applied voltage in the orders of kilovolts. If we are having this electrical condition, then we can say that we can ignite such a plasma. And here in this slide, we have a picture of the plasma. So the electric quartz tube, some metallic copper electrodes. In between these two electrodes, we ignite this kilovolts voltage, and we have this plasma effluent that will go out of this tube. This is the active zone that we can use in the experiments. Here we have a sheet of polymeric foil, and it is exposed to the plasma. Beside this optical image, we have an infrared image, and we can tune up the electrical parameters of the plasma in such a way that we can get even a cold discharge. The red color in this infrared picture is the highest temperature. So we can have such situation in which we can say that this discharge is cold, but also we can make it hotter. If we are looking at this light produced by the plasma through an optical spectrometer, we can see that the plasma have some specific excited species, some of which are called reactive, oxygen or nitrogen species that can be used in the way of starting a reaction on the surface. Of course, we said at the beginning that we are trying to see if the plasma can affect the additive processing. And to do that, we took some commercial polymers, PLA, ABS, PETG, the most known used polymers on the market for 3D printing. And we tried to see if their properties can be changed by the plasma and in which direction. We thought that the best thing to see that is to build up an object, to 3D print an object from these materials and try to test those objects. And of course, to do that, we use several characterization techniques, some of them for the surface, some of them from the bulk material. If we are looking at the surface of the material after we expose it to the plasma, so this column is for the plasma exposed materials, PLA, ABS, PETG, we can see that the morphology is changing. And we know from literature that this is due to the plasma itself. Of course, we are trying to see if this is not the only case. We want to see if this changing in the surface can affect the compactness of the object that we are printing. And here we have some SEM images, and we can see if we are breaking up the object that we printed, that the objects are quite compact. And this is a good thing. That means that each layer that it is deposited, it's sticking to the next layer. Of course, we can also see the surface of the primer material that we expose to the plasma. And of course, we want to see if this change in adhesion can increase the toughness of the material, and we done some tensile strength experiments, and we observed that here in this spider net diagram, the red and the blue areas are for the treated material, and the gray is for the untreated material. We can see that some of the properties of the materials are changed in the sense of the impact strength or elongation at break or tensile strength or even the Young modulus. And depending on the material, we can say that the treatment can increase its toughness, it can increase its elasticity and so on. Of course, we are interested also upon the surface, and we saw that every time we are treating the surface, the water contact angle is decreasing and the energy of the surface is increasing. That means that the surface is more hydrophilic, more stickable to the next layer. That thing is, let's say, to be seen in the surface tension on the total value or even on the polar part. We can correlate this with some time of the treatment of the surface. And of course, we can also somehow relate it to the oxidation process that we can see during the FTIR spectroscopy as well. What was interesting for us was to see if the bulk material is changing, and for our surprise, we saw that after the treatment, some new peaks can be found in the X-ray diffraction pattern. We're still trying to understand what with these new peaks, so still under evaluation. But also we saw that even in the differential scanning calorimetry characterization, we have some differences. Small, but enough to say that the overall melting temperature of the materials is changing after the plasma treatment. And this can help us with the cost effectiveness of the material for 3D printing. To back up the oxidation processes of the surface after the plasma treatment, we also done some XPS measurements, and we saw that the oxygen content is increasing after the plasma treatment. This was no surprise, but it was a scientific verification of the things that we can do to the plasma, to the surface. And of course, we tried to see if this increasement in energy can be related also to some other features that we are interested in. Let's say ink printing on the surface that we are treating. And we saw with some special liquids that after the treatment, we can say that the surface is more printable. This increasement is also important in the biomedical field, and we are trying now to see how stickable some biological molecules are onto the surface. Here, I will just show these two graphs. Here we can see that we have a more adherence of some DNA put it on the surface. for the treated polymers into the plasma in respect to the polymers that are not treated in plasma. We have some publication in this part and some undergoing. To conclude my research, our group research, we can say that we now are able to use such a plasma device in order to modify the surface of some polymers. We can tune up this plasma source in such a way that we can have specific properties to investigate at the end of the study. We can say that the plasma treatment of the polymer sample is good with no byproduct whatsoever in the respect of chemical waste. We can see some small differences, but important for the material characterization in both XRD and DSC measurements. And of course, we can see an increasement in the adherence of the material during the 3D printing process. We have to thank our sponsors for the work, and these are some of the students that are working in our lab. Thank you for your attention. I hope I was not so too fast with the presentation.
No, we thank you. Are there any questions? Yes, please. Dr. Curțaru, but please come here.
Hello, my name is
Hello.
Elena Curțaru. Very nice presentation. Can I ask you how did you put the DNA on the surface of the polymers, of the 3D printed polymers?
Okay, so here is the small schematic of it. We extract some DNA from helicat cells, and we just put it in solution. Here are some examples. We printed the material in round shape, in disc, and we put it there, the solution of the DNA, and we bake them at 37 degrees for, I believe, 1 hour, and afterwards we read them.
Okay, and the application would be?
We are trying to see now two directions usually used for polymers. For biosensors, so we want to stick some biomolecules on the surface, or we want to move to the repellent materials for, let's say, medical investigations and so on. So either we can make the surface to repel these biomolecules or to attach them better. For us is to attach them better in the sense of a biosensor.
Thank you.
Thank you.
Okay.
It seems that we have another questions from the online audience. Please. Yes, please, from the online, you can ask, but Mr. or Mrs. Siddhartha, please turn on the microphone, please.
Check the small microphone on your screen.
Mr. Siddhartha, turn on the mic, please. Tu nu poți să-l deschizi.
If not, he or she can write me in the chat option.
He did already.
Good morning, Dr. Andrei. If the materials are amorphous, then how can we find the degree of crystallinity on the materials? May you please explain? It's very helpful for me.
Okay, so usually we know that polymers are amorphous. but it is accepted that a specific degree of crystallinity can be found in the sense that during the polymeric sheet, we have some domains of crystallinity. We can say that we cannot find perfectly amorphous materials or perfectly crystalline. There is always a small amount of the other part. So in polymers, even though they are known as amorphous material, we have a certain degree of crystallinity. And based on the X-ray diffraction characterization, we can find this. The formula to do that is here. It's like in the other metallic or composite sheets that are investigated in the X-ray characterization. So if the material is more crystalline, then we can say that we need a higher temperature to melt the polymer. In our case, if it is more amorphous, the temperature of melting the polymer is lower. This helps us in, let's say, making an estimation of consumption of a 3D printing process. So if the material is easy to be melted down, that means if we have a 3D printing farm, let's say 100 3D printers, then the consumption of energy to build up some plastic object with this printing farm is lower, so it is more effective. I don't know if that helped with the question.
He said okay.
Yes, it seems that Mr. Siddhartha heard your.
Okay, I saw it also in the chat part.
Yeah. Thank you, Dr. Năstuță.
Thank you very much for having me here.
We thank you. Right now, we start with the presentations in section 1. This section is chaired by myself. My name is Motoc Adrian, and near me is my colleague Dr. Drăguț. But before starting with the presentations in section 1, please allow me to remind you once again the sponsors of our event. And I mean here the Ministry of Education and Research, the European Technological Platform on Sustainable Mineral Resources, and the two Romanian companies, Nanoteam and Altium. So, if Mr. Constantin Cătălin Paul can hear us? Okay, great. Sorry. I will ask you to sit in my place. No. It is better for the online.
I think it's okay. It's okay. You can, if you want to.
Yeah.
Okay. 1 second to share your presentation.
Good morning, everyone. I am pleased to be here. I will not change the topic, and I'll talk about polymers used for electrochromic and energy storage applications. The need of modern technology has determined the scientific research to develop new materials to be used in diverse technological areas. One of the most important class of high performance materials are polymers. A particular class of polymers are those used for electrochromic and energy storage applications. These polymers are characterized by the presence of an electroactive unit where triphenylamine is one of the most used moiety. Unfortunately, triphenylamine reached its maturity, and in this context, we tried to find another electroactive unit. And in our quest, we found phenoxazine, which is commonly used as whole transporting material in many applications. Phenoxazine unit is known for its reversible oxidation process. It generates stable radical cations, is a strong electron donor moiety, and present interesting electroactive and electrochromic properties. The polymers built on a phenoxazine unit are commonly used in solar cells, in memory device, organic light emitting diodes, flexible displays, and field effect transistors. Having these highlights, we plan a strategy to design and synthesize a phenoxazine and diphenylamide based polymers, and then to investigate the structural properties relationship, to establish the superior performer among 3 categories of polymers, and to build a laboratory scale electrochromic device with energy storage capability. For this purpose, we use the starting materials: pyromelithic dianhydride, terephthaloyl chloride, and terephthalic aldehyde were obtained from commercial sources and used without purification, while the diamine was synthesized in our laboratory. The diamine incorporates some important structural elements to improve the electrochemical stability. The structure is in a tape model with a double electron donor core and aliphatic chain to enhance the solubility of the polymers. The diamine was synthesized according to this scheme, and while the structure was confirmed by NMR and IR spectroscopy. For example, in the NMR spectrum, the diamine showed the corresponding signal of the amine functional group. Based on this diamine were synthesized 3 categories of polymers: polyamide, polyimide, and polyamide by polycondensation reaction following different reaction conditions. The structure of the polymers was also confirmed by NMR and IR spectroscopy. In this example, the polyamide showed the corresponding signal of the amide group at around 10.5 ppm. It was tested the solubility of the polymers. The polyamide and the polyimide were soluble in polar solvents, while the polyimine was also soluble in chloroform. Also, the polymers showed high molecular weight, typically for the class of polymers they belong to. Then we test the thermal stability of the polymers so that we can prove that they meet the criteria for use in optoelectronic applications. And the polymers showed good thermal stability. Sorry, here, and also high glass temperatures. We recommend them that they're used in optoelectronic applications. Since the polymers incorporate donor acceptor moiety, we characterize them from optical point of view. And with the help of some DFT calculations, the polymers show some electronic transitions, typically for the charge transfer complex, and those belonging to diphenylamine and phenoxazine unit. But these transitions are not in the visible region of light. And recommend these polymers to be used in optoelectronic applications. Then we evaluate the electrochemical aspect of the polymers. First, we made the differential pulse voltammetry in various important electrolytes, including various salts and solvents, and lithium perchloride and acetonitrile proved to be the most suitable supporting electrolyte. With this condition, we move forward and we evaluate the cyclic voltammetry of the polymers at various scan rates, and we can see that the polymers didn't highlight any secondary reaction except the two main oxidation processes belonging to diphenylamine and phenoxyazine unit. Then we test the stability of the polymers up to 500 cycles for the first oxidation state, as well as up to 100 cycles for the both oxidation state. Since the polymers change the color during each oxidation process, we plan to investigate the spectral electrochemical aspects. So the polymers deposited on ITO substrates were subjected to various potential with 50 millivolts increment. As the potential increased, the new absorption bands started to appear in the near and visible region of light. And it was associated with the change to green color of the film. Then, as the potential increased higher, new absorption bands started to emerge also in the near region of light. Also associated with the second oxidation process and changed the color to blue. Then we tested the stability, the main electrochromic aspects, including the efficiency, the time response. The polymers show very fast response towards blanching and coloring, and good stability for both oxidation process up to 1000 cycles. After we investigated all polymers, we get the conclusion that the polyamide will be the most suitable to be tested in a prototype device made in laboratory. So the device includes a sandwich configuration with the polymer as the anode and the cathode PSS layer as the charge storage layer. The device was subjected to various voltage with increment of 100 millivolts, and the polymer exhibited a comparable behavior as the polymer deposit on ITO substrates. With the increase of the voltage, the polymer started to change the color from transparent to green and then to blue. Also, it was evaluated the main electrochromic aspects, including the efficiency, which is good, but it's low due to the high viscosity of the electrolyte used. These aspects influence also the time response longer. Also, we tested the stability up to 100 cycles. Then to test the dual functionality of the device, we evaluate the energy storage characteristics first by cyclic voltammetry at various scan rates. From here, we extracted the capacitance and obtained up to 100 farads per gram. Also, from these curves, we extracted the capacitive and diffusion contribution, and we see that at low scan rates, the diffusion contribution is higher, which is typically for batteries. Also, the energy storage was evaluated by galvanostatic charge discharge by applying different current densities. From the curves, we extracted the capacitance and we obtained around 9 farads per gram. Also, we tested the stability of charge discharge process up to 500 cycles. According to the results, the based on the device based on this polymer showed parameters around the boundary between batteries and supercapacitors. Then we propose a mechanism during charging and discharging of the device. During charging, the polymer is oxidized and the electron are moved from the anode to the cathode and neutralize the Thiophene cycle. During this process, the lithium and the perchloride ions move to counterbalance the generated charges. During connecting a load, the process is reversed. Since the device retained up to 1.7 volts after 2 hours, we plan to test this as an energy source. So we connected the two devices in series, and we put the power on LED, a 3 volts LED for about 30 seconds. Here I have a short video. It's only 30 seconds, but the device is still lighting up to 10 minutes, but the light is very faint. In conclusion, new phenoxazine-based diamine was synthesized, based on which 3 types of polymers were obtained. The polymers were comparatively studied from physical chemical point of view and electrochemical characteristics. Based on the polyamide, it was built an electrochromic energy storage device, which highlight good capacitance and good stability during 500 cycles. The device, the 2 devices connected in series, was able to power up a 3 volts LED. This work was done with the help of this project. Thank you very much.
Thank you, Dr. Constantin. If there are questions? No. From online? Any raised hand? No.
No, raised hand.
Thank you.
Thank you
and
very much.
Good luck with
Thank you.
your future results.
Okay, so we move forward with the following work in section 1, materials for energy. Dr. Florentina Maxim from the
Yes, I am here. Good morning. Good morning. I will share my screen.
Yes, you can see them. Not yet.
Screen.
Until then, I would like Dr.
Can you see my screen now?
Yes, of course.
Okay.
Please, can you full screen it?
Yes. I will put in a slideshow.
Thank you. And also,
Okay.
I would like to ask Dr. Fatin El Farhani to prepare for the next presentation. Thank you. Please, Miss.
Thank you very much. So my name is Florentina Maxim, and I am senior researcher of the Institute of Physical Chemistry, Elie Murgulescu from Bucharest. And today I will present to you our work mostly related to advanced materials development using supercritical water as a reaction medium. My presentation is divided in 3 parts. The first part is dedicated to the background and motivation, including some general consideration and current knowledge on supercritical water and some its applications. The second part is dedicated to our work on supercritical water, and I will conclude and highlight some ongoing and future work and acknowledge all the people who made possible this work. So the supercritical state of a fluid, it's considered the state in the pressure temperature space is the end of the vaporization curve when the liquid and the gas reach the same density, which is considered the critical density. So for water, these are the values for the temperature, pressure, and the critical and the density. It was a vivid debate if there are some phase transition in the supercritical region which can explain the drastic properties changes, especially near the critical point, as the meniscus in between the liquid and the gas, which is visible in the subcritical region, are not anymore visible at the supercritical state. But since 2010 were demonstrated both experimentally and theoretically that the supercritical state of the fluid is divided in two regions, is the gas-like region of the supercritical fluid and the liquid-like region, regions that are divided by the so-called Wiedom line. Actually, by crossing the Wiedom line, we can observe a phenomena that it's called pseudo-boiling, which is resembling the boiling in the subcritical region. But the difference in between boiling and pseudo-boiling is that the energy given to the system is consumed both for the structural changes, but also to increase the temperature of the fluid. Because of that, there are two terms of contributions to the pseudo-boiling. So it's a structural one and a thermal one. And the strength of this phase transition, it's practically determined by this supercritical boiling number, which is the ratio in between these two contributions. Based on this supercritical water application and mostly on its solvent properties, which so under supercritical water condition the inorganics are precipitated and the organics are highly miscible with water. Supercritical water finds some efficient applications, let's say. So we can obtain clean water by desalination on oxidations. We can obtain functional nanomaterials by synthesis under supercritical water conditions. And also by gasification of biomass, we can obtain hydrogen or methane, so combustible gas. The processes under supercritical water conditions are the main advantage is the efficiency, because the processes are very fast, they are effective, they are selective for desirable products. You can also control the structure and size and shape for the nanoparticles, and mostly the end-up products are harmless, and in the case of desalination is a process of zero liquid discharge. Of course, like everything in life, there are some drawbacks also. And the implementation of supercritical water technologies at the large scale face some challenges still, which are mainly related to the high parameters operation, high temperature and high pressure. It's especially in the oxidation under supercritical water condition is a corrosive environment because all the inorganics are precipitated in the supercritical water streams. The salt deposition causing plugging and fouling of the pipes, it's considering a problem, of course. In the case of catalytic gasification of biomass, the catalyst deactivation by the presence of heteroatoms in the supercritical water streams is also an issue. But there are also solutions, and most of them are related with the optimization of the operating parameters and also the development of functional nanomaterials which can act as catalysts or sorbents. Within this framework is our work. So we aim to generate fundamental knowledge, especially of supercritical water pseudo-boiling phenomena. So in the region where the applications are done in the where this phase transition is appearing. and also to develop functional nanomaterials to address the catalyst poisoning during the biomass gasification process. Most of our work is done using NISA setup. It was a setup developed under my postdoctoral work at Paul Scherrer Institute in Switzerland, and is dedicated to in situ measurements using neutron imaging. The main components of this reactor, of this setup, are the continuous flow tubular reactor, with embedded heater and preheater. Then the fluids, it's feeded in the reactor upwards by high pressure liquid chromatography pumps. The pressure in the system is built and controlled by the back pressure regulator, and all the system is remotely controlled, and data are acquired via data acquisition software every 10 seconds. As I said, our main, let's say we based most of our experiments on in situ measurements using neutron imaging. We did this at the large scale facility at Paul Scherrer Institute, and this method, so using neutron to visualize inside the metallic reactor, it's a very it's a good method to analyze hydrogen containing compounds like water is, because neutron absorb very much the neutron are absorbed very much by the light elements, but they pass through the metallic walls. Like this, we were able to visualize the water flow inside our reactor. And by some imaging processing, we transform these raw images in water density maps. And only for visualization purposes, we apply a color scale in which the density corresponding to the liquid-like state of the water are appearing reddish, and the water in the gas-like state is yellowish. Of course, we determined the temperature of the pseudo-boiling transition by experiments. We analyze practically the temperature profiles, the water temperature profile inside the reactor by analyzing the temperature variation with the time of the experiment. Our materials were developed or produced by supercritical water impregnation method, and so we produce carbon-supported metal oxides by this method, and we use as a support a porous carbon monolith made of activated carbon fibers with graphitic structures. So these fibers are quite small. The material is low density, but with a high surface area given by the microporosity within the fibers. As a metallic source, we use mostly nitrates, and I put here the chemical reactions under hydrothermal synthesis. And we study the cases of formation of zinc oxide and copper oxides. Regarding the fundamental knowledge on pseudo-boiling transition in supercritical water region, we calculated the thermodynamic data, and we by pseudo-boiling theory, and we see that in the 65 pressure interval, the temperature of pseudo-boiling is increasing by 20 Kelvin. Also, the transitional temperature interval at higher pressure is larger than at lower pressures. But what is very important, at lower pressure, we have this supercritical boiling number higher than the lower pressure. That means that the system is consuming low pressure more energy to overcome the structural changes that to hit the fluid. Based on in situ measurements by neutron imaging, we were able to construct the supercritical water phase diagram. In each point, pressure temperature point is represented by the color scale density image. Like this, we confirm the position of the pseudo-boiling Widom line, which clearly divides the gas-like and liquid-like states of the water. Our experiments, so the determination of the pseudo-boiling temperature by experiment follow the theory. So the temperature of pseudo-boiling is increasing with the pressure, exactly like we observe by experiments. And also we observe what it's also important, that higher is the supercritical boiling number, longer is the time needed for pseudo-boiling transition. So when we are thinking on the efficiency of the process, we must take into account this time needed to overcome this transition. The materials development, we were again based our synthesis preparation of the material on neutron imaging measurements, because we determine the temperature of impregnation based on these measurements. So we were sure that the 250 bars, the isobaric conditions, we did the impregnation, the temperature 648 Kelvin, the water is in the liquid-like state with this dielectric constant, but at 668 Kelvin, water is in the gas-like state with this dielectric constant. So of course, this properties variation in between liquid-like and gas-like determine how the reaction are undergoing. So we studied the effect of the impregnation temperature, and here are presented X-ray diffraction patterns for zinc oxide deposit on carbon support and copper oxide deposit on carbon support. What is very important to note here is that the position of the zinc oxide is independent on the temperature, so either the water is in the gas-like state or liquid-like state. But here in the case of the carbon oxides, the copper oxides were produced only in the gas-like state of the water and not in the liquid-like states. From the SEM images, we can observe that there are different mechanisms of growing related with the temperature of impregnation. So in the liquid-like state of water, we have only one-dimensional zinc oxide or copper oxides materials formed, but not attached, let's say, physically attached on the fibers. But in the gas-like state of the water, we have the real impregnation. So we managed to obtain nanoparticles of metal oxides deposit on the fiber of the carbon support. We tested the same under the supercritical water condition, the sulfur absorption capacity, because we want these carbon supporting zinc oxide materials to function on the sulfur absorbents, so to overcome this catalyst poisoning under supercritical water condition gasification. And we managed to obtain a high sulfur absorption capacity, which is superior performance compared to existing sorbent that are working under supercritical water conditions. So this sulfur absorption occurs via a pseudomorphic replacement mechanism in which the zinc oxide nanoparticles deposit on the carbon fibers are more efficient for sulfur absorption. So in conclusion, we presented the first quantitative analysis of pseudo-boiling, both theory and experiment. We demonstrate that impregnation under supercritical water condition is an innovative approach for the preparation of carbon-supported metal oxides. Is one step in a continuous flow. Is not needed to put seed layer or nor mineralizer, so no needed post-treatments. And also in the sulfur, also the zinc oxide, the carbon-supporting zinc oxide materials had a high sulfur absorption capacity, which demonstrate that they can be used as sorbents for sustainable energy production and waste treatment in supercritical water environments. Based on all this knowledge that we acquired on supercritical water processes, we were able to develop at the Institute of Physical Chemistry the new setup dedicated to the synthesis under supercritical water condition of nanomaterials. The setup is named SINAS from the Romanian Sinteză în apă supercritică. And my young co-worker will present a poster with our first study case in which we were synthesizing zinc oxide nanomaterials by this supercritical hydrothermal synthesis using SINAS. More details in its poster. I did not this work alone, so I would like to truly acknowledge all the people from the Institute of Physical Chemistry to Engineer Cristian Iacob, who is still now giving us technical support, and all the people from the Paul Scherrer Institute, our external collaborator, and thank you for your attention. Thank you very much.
Thank you.
Okay.
Thank you very much for the nice presentation. Are there any questions? Maybe online? It seems that no questions. I would like to make a short comment, let's say like this. It was very interesting to see how the structure of zinc oxide was altered by the supercritical water, but by this synthesis.
You mean the
meaning the XRD, the 100 plane and the 002 plane, yes, how they are altered from the normal standard synthesis.
You see here, you mean?
Yes.
So here in the liquid-like state, we have more one-dimensional. So the Grohe preferential was thermodynamically, but here in the liquid-like state, we have more. If it's here, you see that we have some faceted. You see on. Yeah, the grow it's more like flower-like, let's say, which are deposited on the fiber.
Yeah. Thank you very much.
You are welcome.
So we move forward to the next presentation. Dr. Fatin El Farhani from the Faculty of Sciences from Morocco. Can you hear us? Dr. Fatin, can you hear us?
Maybe he's not online yet.
He's online.
No.
Okay.
I say to move forward to the next presentation, yes. And if Dr. Fatin will be available, we'll continue further. So I'm going to the next presentation. Dr. Lukasz Rakowski, hopefully I said it right, from the University of Krakow. Can you hear us? Dr. Lukacs? Is he online?
He was. Yes, he is.
He is online.
Yes.
Yes. Dr. Lukacs, can you hear us?
No answer from Poland.
We'll try to reach later.
Yeah,
Okay.
we will send.
And I will
him.
go to the next presentation by Dr. Bârdan Marius Vasile from University Gheorghe Asaki from Iași.
If he
Dr.
is,
Bârdan.
Poți să-i scrii lui ăla?
Wait a little bit.
No.
Since the section 1 has this free presentation, we'll wait a little bit longer to see if any of the doctors will get online with us. Okay, so I understand Mrs. Siddhartha, Mr. Siddhartha. That is not on this section.
No, it's not according.
la următoare. Era 11:30.
Yeah, Mr. Siddhartha, we will ask you to wait a little because you are scheduled
For the next section.
in the next section, and it is supposed to have your presentation at a quarter to 12 or at 11:30, something like this.
Okay,
So
okay. See you.
we will ask you to wait a little more. So
I will ask again for
yeah,
Dr. Fatin El Farhani, if you can hear us. Okay. Dr. Lukacs.
yeah, we have the participant from Poland, but
There is no answer online.
he is online.
He is online, but Dr. Bârdan.
Yeah, no.
I propose to wait a little bit longer, a couple of minutes, and afterwards, yeah, I see that we have the coming coffee break, yeah, or short break. But let's wait a little bit longer. Maybe one of the
Yeah,
speakers
the last presentation about aluminothermic fuels, it will be defended but it will be done tomorrow, and it will be not online but physical presentation. Okay, so taking into account this situation, we suggest to have a short coffee break and
Until the next section
see
begins.
you here in 15-20 minutes. Thank you.
Thank you.